Okay, good afternoon, everybody. My name is Ibtihal Abdelaziz. I'm a second year at USC and Carnegie Observatories, working with Anna Panatsa on trying to understand the impact dark matter subhalo interactions impart onto stream morphology. So this is GD1. Everybody has been talking about it. It's our favorite stream. And it has a structure at -40 where you can see an underdensity and a spur. And I'm creating models with 8 free parameters that try to understand get at like how changes those parameters change the stream morphology and specifically GD1. So here are 2 examples of models I'm generating. This one is with 10 to the 6 subhalo, and you can see it's kind of like the impact there. There's a little bit of an underdensity. It's similar to GD1, but if I increase the mass by 1 order of magnitude, the stream looks different. 10 to the 7 is the red one, and it's separated into 2 segments, and the gap is much larger. So I'm trying to understand how changing those parameters leads to different stream structure, and the ultimate goal is we are getting new data from HST proper motion of GD1, and we are trying to use that. We're trying to use that to just find the orbit of the massive perturber and go find it. Thank you.
Hello, everyone. This is Joy Bhattacharya from Ohio State. I'm a rising fifth year working with Annika Peters studying field dwarf galaxies in illustrious TNG50. So these inhabit low mass dark matter halos, which have like virial masses between 10 to the 10 and 10 to the 11.5 solar masses. And as we know, these are mainly located in the field, and these are predominantly star forming, except for 2 subclasses. Those are the backsplash dwarfs, and also dwarfs which reside in these compact dwarf groups, where we see there are like signs of quenching, like for example on this plot on the left, which shows the subhalo stellar mass as a function of the host virial mass. We see that there's the backsplash galaxies are quenched, and they are offset from this like the main sequence comprising mainly of the centrals. And also like we see that these field dwarfs mainly inhabit the voids and other low density environment. Thank you.
Hi everyone, my name is Anna Engelhardt. I'm a rising third year now at George Mason University, and my poster is about creating cores and exploration of central dark matter density profiles with different models of dark matter and subgrid feedback processes. So if you want to talk more about SIDM, CDM, and core formation in halos, come find me at my poster. But I also wanted to briefly advertise some of the other stuff that I've been working on. So I recently co-authored a paper. You can use the QR code to follow that there, where we compare different models of supernova feedback. And this figure up here are the cumulative star formation histories of 4 different kinds of star formation recipes that we're comparing in another paper that's in prep right now. And some of my other interests are ultra-faint dwarfs, supernova feedback, metallicities, and star formation histories more generally. And that'll be it. Thank you.
Hey everybody, I'm Hayden Foote. I'm a 4th year at the University of Arizona working with Gertina Besla. And my poster is about a paper I put out last year focused on using the interaction between the LMC and the Milky Way as a dark matter probe. So many thanks to Robin for giving a nice overview of that earlier. Specifically, I'm interested in the dynamical friction wake that forms behind the LMC as it comes into the Milky Way. And we were interested in exploring what if that wake was instead made out of fuzzy dark matter as opposed to cold dark matter? And more importantly, since the wake is dark, can you actually get any information about the dark matter wake from looking at the response of the stellar halo? And then also, does that look any different, again, in the case of a fuzzy dark matter universe? So I'm not going to tell you the results. I'm going to make you come talk to me. But I'll also point out that I'm interested in stellar streams, local group dynamics in general, and also simulations in alternative dark matter models. Thanks.
Hello, my name is Charles Gannon. Strong gravitational lensing has been used to constrain several categories of dark matter models, including warm dark matter and self-interacting dark matter. My work focuses on attempting to reduce the degeneracy in these probes that occurs between the suppression due to tidal stripping and possible suppression due to novel dark matter physics. I work on this through the lens of semi-analytic models of galaxy formation, particularly Galacticus. I've been looking at the spatial distribution of subhalos as well as the normalization that we can expect from the subhalo mass function in the light of artificial disruption. Additionally, I've been investigating the scaling relations as well. Thank you.
Hello, I'm Nicole Guntanis. I just finished my first year of grad school at Ohio State. Today I'd like to highlight one of the projects I've been working on with Annika Peters, Stacy Kim, and Yvonne Esteban. Here, the goal of the project is we're predicting properties of dwarf galaxies under cold dark matter and lumpy dark matter and comparing them to observational properties of Milky Way satellites. Here, lumpy dark matter is like cold dark matter, but with enhanced power on small scales. So the goal is we want to be able to say which dark matter model best predicts the observations. But another key component of the project is understanding how uncertainties and assumptions in the underlying models affect this comparison between models and observations. And so here is one example of that for cold dark matter. I generated mock satellite populations. The cord ones are in red, the cusp ones are in blue, and the SDSS dwarfs are in black. And so when you have different core cusp mass transition models, it affects our predictions. So it's important to take into consideration model uncertainties.
Hi, my name is Adam He. I'm a rising fifth-year graduate student at USC working with VETA. My poster is about this paper that we put out last year on the archive with postdoc Rurian, who's here, and Misha Ivanov at MIT, who's not here, but he wishes he could be here. And we looked at this really interesting self-interacting neutrino model and analyzed it with a combination of CMB and large-scale structure data. And we found that it actually, after you analyze it with all that data, it actually gives this interesting 5 sigma preference for this model over lambda CDM. Please come talk to me more about that if you want to learn more. I just put this one figure up to kind of show how that preference is really achieved. It's really because this model, this is the power spectrum for the specific model divided by the vanilla lambda CDM power spectrum. You really see this steep suppression or decrement of power towards smaller scales, which is how it is able to fit the Lyman alpha data. I shall finish now because I'm out of time, but please come talk to me.
Hi, I'm Hyun-Soo Kong, a sixth-year graduate student from UT Austin working with Mike Boylan-Colchin. My scientific interests are all things small scale, basically. So small scale tests of lambda CDM, especially on the CDM side. That includes making predictions for indirect detections of dark matter substructure, and that also includes galaxy formation and evolution, including reionization. You should ask me why I think reionization has anything to do with dark matter physics. I think they're very tied together. And I do that all in cosmological simulations, and we've heard from Robin today at some length that using the standard pipeline of tracking subhalos doesn't really work, especially if you're looking at things that are relevant for ultra-diffuse satellite galaxies or addressing the question of ultra-faint satellite galaxies in the Milky Way. So I made a package that addresses that problem. I have a poster out there, so please come talk to me.
Hi everyone, I'm Charlie Mace at Ohio State working with Annika Peter. So lately I've been working on N-body simulations of SIDM dark matter halos, specifically core collapsing halos that you've heard about in the last couple of talks. Now if you want to use these simulations to, for example, model these halos for gravitational lensing, which is also something I'm working on, you have to be able to trust your results and know you're seeing converged, accurate results from your simulations. So recently, and in the poster I brought here, we've been working on convergence testing for these simulations, testing a few numerical parameters, like the number of particles, the softening length, and the time step size. Our poster focuses on the, for us, startlingly high resolution requirements we found for core collapse. But here's a little, very small sample of our full data set. Talk to me or check out the paper if you want to hear about the rest of our results. Thank you.
Hi, I'm Granos Karimi, a fifth-year PhD student at the Technical University of Munich, in collaboration with Simone Biondini from the University of Basel and my professors Pinura Brambilla and Antonio Vairo. The poster that is outside shall give an overview about a recent theoretical work we've been working on, namely the recoil effect that can arise due to the center of mass motion of dark matter pairs in the early universe. And we are especially focusing in the regime where the chemical freeze-out happens, where it is assumed that the dark matter pairs initially are and still stay in kinetic equilibrium. So they have non-vanishing center of mass and relative momenta. And we are studying exactly this evolution with the motion of the center of mass and its effects on the thermal rates that arise during the chemical freeze-out and afterwards. And moreover, the recoil effects are seen from different kind of frames, okay? Laboratory frame, center of mass frame. Yeah, and we study its effect also on the relic density abundance. I would be happy to talk about it if people are interested. Thanks.
Hi, I'm Sid. I'm working with Andrew Benson and Ethan Adler at USC and Carnegie. And my poster outside is just about looking into Denning's parametric model, and he's back there if you guys want to ask questions about that too. And this parametric model basically lets us take CDM halo properties like Vmax and RVmax and create a hypothetical SIDM halo. And this model is really well within like 10%. And there are some halos in some simulations which the model overpredicts core collapse sooner than expected. And I'm basically looking into adding maybe some effects of mass accretion rate onto how like the model works to kind of converge those results. And there's some promising results, so that's basically what the poster is about. And other things I'm interested in are just how merger events affect core evolution and a parameter space that kind of helps us see the effects of mass accretion and merger history on the core collapse process. So, yeah.
Hi, my name is Isabel Sands. I'm a third-year grad student at Caltech working with Phil Hopkins. My poster, and I'm lucky that I don't have to explain about the diversity problem because we just heard about it. I explore the possibility that in dwarf galaxies, rotation curves can fail as tracers of dark matter due to mostly time-dependent effects like bursty star formation, galaxy mergers, strong magnetic fields. I have some examples up on the slide. I have other interests, mostly pertaining to galaxy scale tests of dark matter. I'm looking at some simulations of galaxies with cosmic ray spectra in order to investigate the galactic center gamma ray access. I'm gearing up to do some alternative dark matter simulations with long-range self-interactions. And I'm also interested in seeing what we can learn about dark matter just from raw H1 radio data cubes without inferring the rotation curve. Thanks.
Hi, I'm Eleanor. Is this good? Okay. I'm a second year
PhD student at USC working on this project with Chris Pardo called Constraints on the Dark Matter Baryon Interaction Cross-Section from Galaxy Cluster Thermodynamics. And so the way that we're approaching this problem is first by looking at the approximation that galaxy clusters at low redshifts are approximately in thermal equilibrium. And then I go and look at what the cooling rate due to dark matter baryon interactions would be, from baryons losing energy to dark matter through velocity independent interactions. And then I combine this with the major thermodynamic processes in galaxy clusters to come up with a limit on basically how much the dark matter and baryons are able to interact without taking the galaxy clusters out of thermal equilibrium. And so this plot comes from applying that model to one galaxy cluster, and we can talk about it more later.
Hi, I'm Carton Zeng. I'm a grad student at Ohio State, working with Annika Peter, and I'm going to start as a postdoc at Texas A&M starting this fall, if I don't mess up my thesis defense next month. So I work on controlled simulations of SIDM with a focus on tracing the evolution of subhalos from core creation to core collapse. So our aim is always to invest all the computational power into resolving small subhalos, which can be very expensive, especially when it's near core collapse. So my poster out there has three pieces of work. In the first part, we developed a new method to trace individual subhalos through their orbital evolution one at a time. And in the second part, we make it a population and look into the ensemble properties of these subhalos. And in the last part, we populate the individual subhalos with stellar particles, trace stellar properties. Thank you. And I'll talk about some of the stuff next week in the regular program.
Hello everyone, I'm Yao Zhang, a PhD student from Tsinghua University. Thanks for giving me the opportunity to introduce our work. We know that in warm dark matter models, the small-scale structures are suppressed, but we propose a new method to constrain warm dark matter on large scales. We found that the post-reionization Lyman alpha forest and 21 centimeter power spectrum are distinguishable among different warm dark matter models on large scales, as shown by the colored lines in the middle panels. And how to achieve this? The key is the reionization relics. The relics can couple the small-scale post-reionization evolution and ionized bubble scales. And if you are interested in more details, please come to my poster. And we also made some MCMC forecast for the future surveys, and that's the results. Thank you.
So that was our final flash talk. As you can see, the future is bright. There's some incredible work being done by our students here, and I really encourage you to engage with them, especially now that you've heard the flash talks and know that the posters are on the way to the food. So with that, I will release you all to lunch, and we meet back in here at 2 o'clock.